Hi everybody, welcome back to Multirate Signal Processing. Today lecture 3 about computing the frequency response. So if we have coefficients of a finite impulse response filter, H, or in general the impulse response, its frequency response becomes, using the discrete time Fourier transform, this equation. So here we can see we have our impulse response, or the coefficients of our finite impulse response filter h of n. And then we just apply the discrete time Fourier transform in this way. Right? So here we have the transform kernel, and then here, using the normalized frequency omega, we obtain the frequency response. And even if h is real valued, this transform kernel is complex valued. So in general, the frequency response will be complex valued. So here we already have two different ways to describe a system or a signal: by its impulse response in the time or space domain, this is this h of n, depending on if it's audio or images, and by its frequency response, h of omega, right? Because we can invert this transform. It doesn't really matter if we have the frequency response or the impulse response, because we can convert between the two. So they are related by this discrete time Fourier transform. So an example, if we have an amplifier which is described by its frequency response, including the phase, then we can obtain the time domain version, its impulse response, by taking the inverse Fourier transform of its frequency response. This can be seen as the output of our amplifier if the input is a single impulse, because an impulse has a flat spectrum and hence the name impulse response. The output of the amplifier is then the convolution of the input signal in the time domain with its impulse response, right? And convolve something with an impulse is again the same. So this is how you get the impulse response. But remember, in practice, you usually wouldn't use an impulse because in reality, often the impulse doesn't have enough energy to get a good signal-to-noise ratio. So in practice, usually an impulse is not used. It has not enough energy, or it could destroy the system if you put enough energy in it. But often white noise is input to our amplifier, and then the output is Fourier transformed to obtain its frequency response. So white noise again has a flat spectrum, right? Or at least on average it has a flat spectrum. But here the energy is distributed over time. So in this way we can put enough energy into our system without concentrating it in just a single pulse which might destroy our amplifier. Right, so white noise has the advantage that it has more energy without destroying the system, and it has an approximately constant spectrum like the pulse. Another often used method is a sweeping sinusoid with increasing frequency and constant amplitude. This often gives more precise results, but takes longer to measure. The resulting measured frequency response is then inverse Fourier transformed to obtain its impulse response. If we have the Z transform, we obtain the frequency response of our system or signal if we simply replace Z by e to the j omega. In this case, the Z transform becomes the DTFT. The transform formulas actually become identical. And this is like reading out the Z transform along the unit circle in the complex domain of the Z transform. So this can be seen here. So here in this image, you can see the complex Z-plane. Here is the real axis, here is the imaginary axis, and then around the origin we have this unit circle. And this unit circle is covered by e to the j omega. right? It's actually a plus, it should be a plus here. So if we have a positive omega, then it goes up. And with omega equals pi over 2, we get a purely imaginary point here. So, and then if you continue, omega equals pi, you're at -1, and -1 corresponds to the Nyquist frequency. So remember, omega equals pi, the normalized frequency omega equals pi means half the sampling frequency, and which is the Nyquist frequency. So here you can see that actually this normalized frequency can also be interpreted as an angle, right? And this is basically the connection now to the complex z-plane. Remember, before we defined our normalized frequency such that 2 pi corresponds to the sampling frequency, and since we have a sample system, it's 2 pi periodic, so quite well fitting. And here we can see that this normalized frequency now can also be interpreted as an angle to the real axis. So here we have Nyquist frequency, and then when we go on, we come back to omega equals 0, and this omega equals 0 is then identical to omega equals 2 pi. So fits perfectly. So this unit circle now also covers this 2 pi periodicity of our frequency domain of our sampled signal. So yeah, so you just have to remember, in this case, in the complex z domain, this normalized frequency omega now also has this other meaning of being an angle in this complex z-plane. And this is also, it makes it easier to visualize. Each frequency now corresponds to an angle and to a point on the unit circle. Right, so this is what I just said. The periodicity of our frequency domain can also be seen easily here. Remember, frequency pi corresponds to the Nyquist frequency, and 2 pi is the sampling frequency, which in the time discrete domain is identical to frequency 0. So yeah, it's identical to frequency 0 because we don't know what the signal does between the sampling instances. Right. So here we can see that in general we obtain a 2 pi periodicity in the frequency domain. For real-valued signal, the upper half of the circle has a frequency response which is symmetric to the lower half. It's actually conjugate complex, and hence, strictly speaking, we get some sort of pi periodicity for real-valued signal. So hence, Nyquist theorem, which states that we only can construct frequencies below half the sampling frequencies, half the sampling frequency for real-valued signals. Yeah, so if we have frequencies from 0 to pi, this is sufficient to reconstruct our signal because we know the negative frequencies from 0 to minus pi are basically the same, except that it's conjugate complex. Yeah, so hence for real-valued signals, only one half of the unit circle is unique. For complex signals, it's a different story. So in that case, both halves of the unit circle can contain different frequency responses, and hence there we indeed have a 2 pi periodicity, and we could reconstruct frequencies up to 2 pi. So here really the entire frequency range from minus pi to pi, including the negative frequencies, or from 0 to 2 pi, because of our 2 pi periodicity, is needed for complex signals. We can imagine complex signals or frequencies as consisting of two signals, one for the real part and one for the imaginary part. For instance, in stereo audio signals, the left channel could be seen as real part and the right channel as an imaginary part of a complex audio signal. The same for negative frequencies. So take e to the minus j omega n. They consist of a cosine real part and a minus sign imaginary part. Right, so if you decompose this into real and imaginary part, you can see it's cosine omega n and minus sine omega n. So this unit circle, if it describes an input signal x of z, for instance a certain frequency, is the input to the z transform h of z by replacing the z by e to the j omega to obtain the frequency response h of e to the j omega. You can imagine, for instance, the magnitude of the resulting frequency response as an additional dimension on top of the circle that we just saw of the z-plane. So we have the circle in the z-plane, and then the magnitude is, for instance, perpendicular to this circle if you want to plot it. So if you plot the frequency response for real valued signals, for instance in Python, what is usually done is to plot the upper half of this unit circle. For real valued signals, the lower half is symmetric to it. Right, and this is how we can analyze filters now. So we know if we have a real valued filter, it's sufficient to look at the frequency range between 0 and pi, the positive frequencies. So here's an example, a very simple filter. A simple filter which consists only of two coefficients, and this filter acts like a moving average operator. So we have an input signal, x of n, and the output of our low-pass filter is then y of n, and it can be computed as in this formula. So here you can see it's basically the running average of the past two samples, x of n and x of n minus 1. So for each time step n, it computes this average of the past two samples. And this is kind of a cheap low-pass filter. So what is the corresponding impulse response of this filter? It is the response of the system to a unit impulse, right? Hence the name. So we can just make a unit impulse sequence. So we set 1 to the first sample of a sequence, and then it's followed by zeros everywhere else. So then we can now simply compute the output step by step. So we have y0. This would be the first sample of our impulse response is 1/2. When we look at our equation, x of 0 is 1, x of minus 1 is 0. So what's left is this 1/2. Right? And then we look at the next time step, n equals 1. So again, look at the equation. Y of 1 is 1/2 x of 1. So this now becomes 0, disappears. And this is x of 1 minus 1, x of 0, and x of 0 is 1. So we have 1/2 again. Right? And everywhere else, it's 0. So this can also be written as a vector. So here this vector now is h, and it contains the impulse responses. So, and since it's a vector, it should actually be boldface to be consistent. So here we have this vector now, boldface. So it contains those two coefficients, 1/2, 1/2, the ones that we computed here, and the rest was 0. So that also means that now we can compute the output as a convolution of this input with this impulse response h. So this equation here, y equals x convolved with h. So the output is then the same. And this convolution can now also be written as a matrix multiplication. So the convolution or filtering operation can also be written as a multiplication of the signal vector and the so-called Sylvester matrix, which you can see here. So here you have a long vector of the input, right? So here you have your x, all on this long, possibly infinitely long vector. Then here in this matrix, which possibly also has infinite extent, you can see the coefficients of our filter. And now you can see here at the matrix entries that the coefficients are shifted. When you go down, that means you go to later times for the output, and then the impulse response is shifted by one sample for each row. And in this way, we basically implement the convolution as this matrix multiplication. Yeah, we can also use this matrix formulation, which is a little bit more practical because it has, in this case, the finite impulse response as a finite vector here from the right-hand side. So now here the coefficients appear as a vector on the right-hand side. And then the matrix contains the signals as far as it concerns the filter. So you can see here in this row, it contains the two samples for time step 0, which are then multiplied by the coefficients here. So in the next time step n equals 1, you see the input values which are multiplied now by the coefficients and so on. So here you can see now the signal basically is shifted by 1 for each time step. So again, we get the convolution written as a matrix multiplication. And I will continue to use this matrix formulation for now on, because this is a very practical representation, because often matrix multiplications are more conveniently mathematically than convolution. Right. So next let's take a look at measuring the frequency response, or computing the frequency response of this moving average filter. We can simply now compute the z-transform of the impulse response, the coefficients. Right, here you can see it. Here's the z-transform of our coefficients h of n. So here you can see in general the z-transform, it goes from 0 to infinity, but since we only have two non-zero coefficients, that means we only keep two summands, right? 0.5 times z to the minus 0 plus 0.5 times z to the minus 1. So really simple in this case, because we have just two coefficients. So now replacing this z by e to the j omega gives us the frequency response of this low-pass filter, which you can see here. So same sum, except now instead of z we have e to the j omega, so that turns it into e to the minus jn omega. Right. And when we plug in the coefficients, here z to the 0 still remains 1, and here we have 0.5 times e to the j minus j omega. So this now is really a simple expression which we could directly plot in Python now. So this is now the complex frequency response, and you can see that it's complex because e to the minus j omega is complex valued in general. So often we are interested in the magnitude or absolute value of this frequency response because we would like to see how much of a signal at a certain frequency is attenuated. Like when we have a low pass, we want to attenuate the high frequencies. And high attenuation means low magnitude values at those frequencies. An example might be an equalizer filter, which has the goal to obtain an overall frequency response which has a flat magnitude, for instance, to equalize an audio amplifier. If the amplifier has, for instance, an attenuation of 0.5 at a certain frequency, we need the equalizer filter to have an amplification of magnitude 2 at that frequency to compensate for it. In this way, we obtain a constant magnitude of amplification at all frequencies. Yeah, and this is basically the magnitude of our frequency response, right? In this case, we neglect the phase of our complex frequency response. We focus on the magnitude just to have the same strength of all the sinusoids in our mix. Yeah, or to keep the same strength. But observe that the phase of our complex frequency response can still be different for all frequencies. So our magnitude frequency response in this case is this expression here. We take the magnitude of h of omega, and that's the magnitude of 0.5 plus 0.5 times e to the minus j omega. Right, easy enough. So now we can actually compute it using Python and using the z-transform. Right, we saw that we can actually compute the z-transform in Python using SymPy. Right, and SymPy then turns it into a polynomial, as you can see here. So we start with IPython minus pylab. Here we have our impulse response. Here we now prepare for the z-transform. We define the symbol z. And here we then compute the z-transform as polynomial of our impulse response h. Right, so here we simply turn it into a polynomial. Yeah, and then next we basically need to replace the z by e to the j omega, and this is what we do here. So in this case, we don't want to take the continuous frequency domain. We just sample the unit circle. So here we sample it between 0 and pi in 100 steps. So this is then our angle omega. Remember, we just need the positive frequencies because here we just have real valued coefficients. The negative frequencies would be symmetric. So this is then our angles uniformly sampled between 0 and pi. Right. So here we initialize the frequency response with zeros, with actually complex valued zeros, because here multiplied with a imaginary unit in Python, 1j. 1j is the imaginary unit in Python. So this is a predefined variable which represents the imaginary unit. Yeah, so next we replace z by e to the minus j omega. Right, and we do that by replacing z to the minus 1 in the argument. So you can see it. Here I have the for loop for my different omegas. So here k represents the samples of my frequency domain. And then here I have my z-transform h, and here instead of z, or z to the minus 1, I replace it by e to the minus j omega of k. Remember, k is my index for this angle. So this represents my samples between 0 and pi. Right, so this is also what you can do in SymPy. You can simply take this argument, and this argument then replaces the polynomial variable. In this case, z to the minus 1. Right, so in general we would replace z by e to the j omega, but here replace z to the minus 1 by e to the minus j omega. Right. So, to be more correct. Yeah, so then we just can take the resulting magnitude, and that's it, right? So for each frequency sample, we can take the magnitude. You remember this becomes a vector after the loop finishes, and then we can plot it. So we have on the x-axis, we have our omegas, our sampled omegas, and on the y-axis we have the magnitude of our frequency response, which was our z-transform. Then we can assign labels and a title. And before I show you the result, I want to actually show it in my little terminal window here. So let me start with IPython. Nope, I wanted to have IPython minus pylab. IPython minus pylab. And then simply copy and paste. So up to there, copy. Yes, so that works. So here we have omega. You can see these are our frequency samples between 0 and pi, and we have 100 samples in those. We can also take a look at h of z. So h3, our z-transform, simply consists of this polynomial, 0.5 times z to the minus 1 plus 0.5. And our variable for the polynomial is 1 over z, z to the minus 1. Right, as expected. So now we can do this substitution of z to the minus 1 by e to the minus j omega, which you can see here. So first I initialize my h such that it's ready for the for loop. So now I have complex zeros in it, so you can take a look. So it's 100 complex zeros. And I need to initialize it, otherwise with complex zeros, otherwise we would have a type conflict. Yeah, and then I can execute this for loop. So copy, paste. Yeah, it took a few seconds, but now it's done. So now I have h. And now you can see this h contains the complex frequency response, right? So each row here is one sample of this complex frequency response. And now we are more interested in the magnitude. So here we would take abs. Let's see if that works. Yep. So abs of h now gives us the magnitude at each frequency sampling point. You can see here it starts at 1 and then it slowly becomes smaller. And then it disappears here in the last one. But we also see it's not really becoming very small, which also shows that it's really not a good filter because the attenuation is not really good. So we have something 0.1, 10 to the minus 1 is not really much. So that's usually not sufficient. So now we plot it to see it in more detail. So here again I copy and paste. So paste. Yeah, so here you go. So here now you see the resulting magnitude frequency response. And as you would expect from a low-pass filter, it starts at magnitude 1, which means it doesn't affect the sinusoids at those low frequencies in magnitude. It keeps the magnitude of those sinusoids. And then when you increase the frequency, it slowly has more and more attenuation, which means this factor becomes smaller, which means that a sinusoid at those frequencies are attenuated. So if you have a sinusoid at normalized frequency 0.5, which is roughly 1/2 Nyquist, then you go up and then you can read it out. So here on the screen you can see y equals 0.7. So here it would multiply the magnitude of all the sinusoids at that frequency with a factor of 0.7, right? Which is about square root of 0.5. Here you can see that those sinusoids become attenuated a little bit, but not really much. It's only when you come close to Nyquist frequency, so down here, so here I'm very close to Nyquist, then I have a smaller, much smaller factor. So only right in the end we have a good low-pass filter. Right. Yeah, so this is what we see here again. Yeah, and especially for the attenuation, for the small values, the dB scale is very practical because it shows the magnitude in more detail for small values, because the dB means we apply the logarithm, right? And the logarithm means we see small values better. So here we can see that we apply the log for voltages or currents with a factor of 20. So instead of just taking the magnitude or the abs of H, we apply the logarithm of base 10 and multiply it by this factor of 20. So this is how our dB for voltages or currents is defined, and here we assume we have something like voltages, right? When it comes from the A to D converter, usually it measures voltages, say, from a microphone. Yeah, here I specify the range for the axis. So here it should start at minus 40 dB and goes up to 0 dB. 0 dB means a factor of 1. So look at this formula. If abs of H is 1, then the log of 1 is 0, right? So in this case, if you take a look at the inverse, 10 to the x is 1, so x must be 0. 10 to the power of 0 is 1, right? So that's why the log of base 10 of 1 must be 0. And since this is the maximum that we get from our magnitude, smaller values must be below 0, and that means here negative, right? So here we have the scale. I set the scale to be between minus 40 and 0 because that's where most of the interesting parts are. And it goes from 0 to pi, the Nyquist frequency. So again, I copy and paste, copy and paste in my window. And now you can see it, right? So now you can see the attenuation in dB. So here we have minus 20 dB. So what is minus 20 dB for the magnitude of H? So basically we have to convert back, right? Remember, dB was 20 times log base 10. So first, to get the log base 10, we need to divide by 20. So minus 20 divided by 20 is minus 1. So minus 1 is log base 10. And then we have to apply 10 to the power of this to get our magnitude. So 10 to the minus 1 is magnitude of H. So in this case, 10 to the minus 1 is 0.1. So minus 20 dB here is 0.1, and then we can see here it's actually pretty far down here. It's very close to Nyquist. So here we see it's 2.9 on our normalized frequency scale. So it's almost Nyquist. And 20 dB minus 20 dB is actually not much attenuation. So if you have, say, aliasing artifacts, then minus 20 dB is usually not enough to attenuate them enough to not be able to hear it. So 20 dB attenuation is audible, but usually you can still clearly hear what was attenuated. Usually you say minus 60 dB is good enough to make something inaudible. So 60 dB is a good rule of thumb, and you can see here it's not even on the scale here. Here we end at minus 40. So we see here our filter is kind of disappointing. It's not really a good low-pass filter. But this also shows you when you evaluate a filter, usually what you do is you plot it in dB, as I did here, right? Because then you can more easily see the quality of attenuation that you get. Yeah, so here's again the same plot. And you can now also analyze the phase, right? And for the phase, we have the function angle of h. Right? Remember, the phase was the angle between the real axis and our point on the unit circle. Right? This is now the phase that we get for the magnitude response here. So we apply this phase angle to the output of our frequency response, or the output of our filter. Right, so since we have not only magnitude, but we have a complex value, and this complex value has magnitude and angle to real axis, or phase. In this case, it's called phase. Right. So here we compute it. It simply takes the real part divides by the it takes the imaginary part, divides by the real part, and then takes the inverse tangents to get the angle. Right, so we can again plot it. First copy and paste. So that's it. And you can see it looks actually quite simple. Right, it's the straight line. So here you can see again the normalized frequency, and vertically now is the phase angle in radians. Right, so here you can see we have minus pi down here, minus pi over 2. Yeah, so minus pi over 2, remember, was 180 degrees. Minus pi over 2 is actually 90 degrees, right, minus 90 degrees. And that's half the Nyquist, would correspond to half the Nyquist frequency, but here it's not really related to the frequency, but really just the phase. Right, here we really have the phase, which means a delay of our sinusoid. Right, so it, in this case, when you look at it, here this pi over 2 appears fairly down here, close to, it's actually right at the Nyquist frequency. So the Nyquist frequency would be shifted by minus pi over 2, or accordingly delayed. And lower frequencies are less shifted. Yeah, so this phase is related to a time shift that we get through the filter. And here we have a linear phase. You can see we have a straight line, so it's a linear function. The phase is a linear function of the normalized frequency, and when we have a linear function, that results from a fixed time shift. Right? When we have a fixed time shift, we will get a linear phase. So that's kind of nice here. So all frequencies are delayed by the same time amount. Yeah, and instead of using the z-transform, we can now also use the function frexy, which is a built-in function from our signal library, SciPy signal. So that has the function frexy. And frexy is actually doing the same thing that we just did, just faster and more efficient. So here you can see the result. Well, the argument first is again our coefficients, the impulse response h. And the result it returns is h, capital H, which contains the complex valued frequency response sampled at frequency points which are in this array omega. So pretty much like we just did. Yeah, and then let me try it. Copy and paste. So here we have H. Oops. Yeah, here we have H. So here you can see it's again complex valued, but it looks longer. Let's see. H dot shape. Let's see how many entries we have. Yeah, so instead of just 100, we now have 512 samples. So FragZ by default computes 512 samples between 0 and pi. And we can also then plot it again. Plot of omega, comma, abs of H. Yeah, so you get pretty much the same plot here. We don't even see that we have 512 instead of 100 samples. Yeah, so FragZ uses actually a zero-padded signal H. So it takes H, or two coefficients, and then adds zeros such that it can apply a longer DFT to it. Right, and in this case we want to have 512 samples between 0 and pi. That means the DFT needs to be of length 1024 because it covers the entire frequency range between 0 and 2 pi. So that means we need to zero pad our signal H such that we get an array of length 1024. So that's actually what's done inside FragZ. Right, for the desired frequency resolution. By default, it only computes the positive frequencies. Typo. So here H is an array of complex values of the frequency response, and omega is an array containing the normalized frequencies at which the frequency response was evaluated. So we see that at frequency 0, the magnitude response has the magnitude 1 as before, hence no attenuation, which is important for low pass. And at frequency omega equals pi, it has magnitude 0, which is also suitable for a low pass, right? At least Nyquist, you want to have well attenuated. In between, it behaves basically like a cosine function does. It slowly reduces, so not really like a perfect low pass, which should have frequency response, or should have a frequency response which looks more like brick-shaped, which means we have a factor of 1 at the entire pass band. Let's say factor of 1 at the entire pass band and 0 at the entire stop band, ideally. So it is far from being perfect, a perfect low pass filter. Yeah, we also have the phase of the frequency response. We see that it is a linear function, which I just mentioned, which is particularly important for image processing. The phase is the angle of h of omega. The vertical axis on a dB scale let us see the small values of the stop band better, which works for both power and voltage or current. Observe the dB numbers are using the input of the filter as a reference. Hence the dB number results from 20 times log 10 of output voltage over input voltage. Since the dB scale is so important, you need to be familiar with it. For instance, just memorize a few points. You need to be able to answer, for instance, the following questions. What's the definition of dB for voltage and for power? Right? Voltage has the factor of 20, power has the factor of 10. What is the voltage ratio of 0.1 in dB? Right? This is one of the points that you could memorize because you will see it often. So what's 0.1 in dB? Well, first you apply the log base 10. Right? What's log base 10 of 0.1? It's -1, right? Because 10 to the -1 is 1/10. and then you multiply it by 20 because it's voltage. So you have -1 times 20 is -20. So 0.1, this ratio, say the output is 0.1 volt, the input of your system is 1 volt, then this ratio would be 0.1. So then you can say that this is -20 dB. Yeah, this is basically the answer to the next question. What's the voltage ratio of -20 dB? It's the 0.1. So this is not as straightforward. What's the voltage ratio of 6 dB? Right? And how do you find out? Well, you could use Python, for instance. So 6 dB is not so easy to see. So to turn it into a ratio again, we need to basically invert the dB formula. So we take 6 divided by 20, and then we say 10 to the power. So 10 to the power of 6 divided by 20. And we see that it's not really computing right because it uses an integer division here, so this is better. So here we see the result is actually quite close to 2. Right, and this is also why this is a good point to remember, right? Because this corresponds to a factor of 2 in voltage. So if you double the voltage from input to output, then you have a gain of 6 dB. Right. So that's also good to memorize. Then if you have two systems in a row, one after the other, and the first has -6 dB attenuation, and the next has -10 dB, what is the total attenuation? Well, if you're in the linear domain using factors, you would multiply those factors. But now you're in the dB domain, in the log domain, and in the log domain, multiplications are turned into additions. So here we just have to add those dB numbers. -6 minus 10 results in -16. Right, so total attenuation would be -16 dB. And this is also another advantage of the dB scale, that it's easy to compute a concatenation of systems. Yeah, so if you have trouble with one of those questions, look it up at Wikipedia or the literature and practice. Try out a few fantasy numbers and see what you get and memorize those results. Yeah, now also observe the phase plot. We see the phase response is -ω/2, right? For Nyquist frequency pi, we had -π/2 phase shift. And this is linear in omega with a slope of 1/2, which is why we have a linear phase in this case. And the slope of 1/2 actually corresponds to the time delay. It's actually having a time delay of half a sample. Yeah, hence we also call our filter a linear phase filter, because that's another property it has. Yeah, so next is a high pass example. We can do the same analysis for the high pass filter with the impulse response 0.5 and now -0.5. So it's not the running average, but a running difference. So in the same way as for the low pass, we obtain its magnitude of the frequency response in Python as follows. So here again, we use SciPy signal. We have now this new impulse response. Let me copy it. So this is our high pass filter. And now we can compute the frequency response using our signal frequency function. I copy it because that was the most convenient. So now we can plot it. copy and paste. And this is now the result. And here you can see it almost looks like our running average filter, except that it's flipped between high and low frequencies, right? It's flipped around. So frequency Nyquist looks like frequency 0 for the low pass filter. So it's like if we would mirror the frequency axis. But the shape is actually exactly the same. Yeah. So it shows a close relationship between the two filters. Yeah, so here it is again. So by looking at frequency omega equals 0, we obtain a magnitude of 0. Right, similar for the low pass at frequency pi. And vice versa, at frequency pi, we obtain a magnitude of 1, as you would expect from a high pass filter. Right? But again, between those points, it behaves like a sinusoid, which is far from a perfect high pass. It's a pretty bad high pass. So this looks like the frequency flip version of our low pass filter, as I just mentioned. Okay, and that leads me to the end of this lecture. Thank you for your attention, and then see you next time.